every single thing you've ever experienced, every person you've ever met, every place you've ever been. All of it exists within a sphere that's basically invisible when compared to what we discovered in 2025. The latest space missions have confirmed measurements that will make you feel smaller than you've ever felt before. New lunar laser ranging experiments have pinpointed our moon's distance at exactly 384,472 kilometers, and this precision represents just the beginning of how we now understand our place in the cosmos. Let me show you exactly how impossibly tiny we really are, starting with what seems like the most familiar object in our night sky. Our lunar neighbor gets a 2025 update. The moon appears deceptively close when you see it dominating our night sky, but 2025's precision laser ranging measurements reveal it sits exactly 384,472 kilometers away from us right now. This distance changes by about 3.8 centimeters every year as the moon slowly drifts away from Earth. To put this distance into perspective, you could line up 30.1 complete Earth spheres in the empty space between our planet and the moon. If you decided to walk this distance at a steady pace of 5 kilometers per hour, you would need to walk continuously for 8.7 years without stopping once. A commercial airliner flying at cruising speed would take 17 days of nonstop flight to cover this same distance. When the Apollo astronauts made this journey in 1969, their command module took 3 full days to reach lunar orbit, traveling at speeds that would cross the United States in just 12 minutes. The Artemis program has scheduled multiple lunar missions throughout 2025, with Artemis 3 planning to land the first woman and the first person of color on the lunar surface. These new missions will experience the same 2.56-second communication delay that the Apollo crews dealt with. But modern technology handles this delay very differently. While the 1970s Apollo missions relied on simple radio communications with limited bandwidth, the 2025 lunar missions will transmit high-definition video, scientific data streams, and complex telemetry information back to Earth. Mission Control can now process thousands of times more information during that same 2.56-second delay window. The upcoming Lunar Gateway Station will fundamentally change how we think about this 250,000-mile gap. Instead of viewing the moon as a distant destination that requires a dangerous 3-day journey, the Gateway will transform lunar distance into a permanent bridge between Earth and deep space. Astronauts will live and work in this space between worlds, making the 384,472-kilometer distance feel more like a commute than an expedition. The Gateway's solar arrays will be visible from Earth through powerful telescopes, creating the first permanent human-made structure that we can observe in the space between planets. Recent high-resolution imagery from lunar orbit shows Earth as a brilliant blue marble suspended in the absolute blackness of space. These 2025 images capture details that were impossible to see in the 1970s photographs. You can make out individual continents, weather patterns, and even the thin blue line of our atmosphere. From lunar distance, Earth appears about 4 times larger than the moon appears to us on Earth, but it still occupies less than 1% of the visible sky. The rest is just empty space, highlighting how isolated our planet really is even within our own local cosmic neighborhood. The psychological impact of this distance becomes more significant when you consider emergency scenarios. If something goes wrong during a lunar mission, Earth cannot provide immediate assistance. A medical emergency on the moon means the astronauts must handle the situation themselves for at least the 2.56 seconds it takes for their distress signal to reach Earth, plus additional time for mission control to formulate a response, plus another 2.56 seconds for that response to travel back to the moon. In reality, this means lunar astronauts face at least 15 to 20 seconds of complete isolation during any emergency, and that assumes mission control can respond instantly with perfect information. The precision of lunar laser ranging has improved dramatically since the 1970s. Scientists now bounce laser beams off retroreflector arrays left by Apollo missions and measure the return time with accuracy measured in picoseconds. These experiments have confirmed that the moon moves away from Earth at exactly 3.78 centimeters per year, which means the lunar distance increases by about 1 millimeter every 9.6 days. Over the course of human history, the moon has moved approximately 7.5 meters further away from Earth. This might seem insignificant, but it represents measurable changes in tidal forces and the length of Earth's days. The communication delay creates interesting practical challenges for 2025 lunar operations. Real-time control of lunar rovers becomes impossible because every command takes 2.56 seconds to reach the moon, and confirmation of that command takes another 2.56 seconds to return to Earth. This 5.12-second round-trip delay means lunar rovers must operate with much more autonomous decision-making capability than Mars rovers, which face much longer communication delays. Lunar mission planners must design every procedure around this unavoidable pause in conversation between Earth and Moon. When Artemis astronauts plant their feet in lunar soil, they will be standing in a location where Earth appears as a fixed blue dot in the black sky above. Unlike Earth, where the moon rises and sets due to our planet's rotation, the moon is tidally locked to Earth. This means the same side of the moon always faces our planet, so Earth never moves across the lunar sky. From any given spot on the moon's surface, Earth either appears in a fixed position above the horizon, or it never appears at all. The Apollo landing sites were specifically chosen to keep Earth visible above the lunar horizon for communication purposes. The latest measurements confirm that this seemingly vast 384,472 kilometer distance represents our first tiny step into the cosmic scale. While this distance required humanity's most ambitious engineering projects to cross, it barely registers when compared to planetary distances within our own solar system. The space between Earth and Moon contains absolutely nothing except scattered particles of solar wind and cosmic dust. No atmosphere, no weather, no sound. Just empty vacuum spanning 250,000 kilometers. This distance that seems so impossibly vast becomes almost negligible when we expand our view to include the rest of our solar system. But before we venture further into space, we need to understand just how much more isolated we become when we take that next step outward to our neighboring planets. Mars, the red planet reality check. Mars presents a completely different scale of isolation. The Mars Perseverance rover captured an image in 2024 where Earth appears as a tiny speck of light from the Martian surface. From Mars, our entire planet looks smaller than a single pixel on your phone screen. This photograph shows the view that future Mars astronauts will have when they look up at the night sky and try to spot home. Earth becomes just another star in the Martian sky, completely indistinguishable from thousands of other points of light unless you know exactly where to look. Mars sits an average distance of 225 million kilometers away from Earth, but 2025 orbital mechanics calculations show this distance varies dramatically throughout both planets' orbital cycles. When Earth and Mars align on the same side of the Sun during opposition, the distance shrinks to approximately 54.6 million kilometers. However, when the planets sit on opposite sides of the Sun during superior conjunction, they separate by as much as 401 million kilometers. These orbital variations mean Mars missions must be planned around specific launch windows that occur roughly every 26 months when the planets align favorably for efficient travel. The upcoming Artemis Mars missions, scheduled for the 2030s, will place astronauts 1,044 times further from Earth than the Apollo lunar astronauts ever traveled. While the Moon sits just over 250,000 kilometers away, Mars astronauts will be separated from Earth by a distance spanning nearly 500 million kilometers at maximum. This represents the most extreme isolation that human beings have ever voluntarily accepted. The crew will spend at least 18 months on the Martian surface before orbital mechanics allow for a return journey to Earth. Communication with Mars creates delays that fundamentally change how space missions operate. A radio signal traveling at the speed of light takes between 3 and 22 minutes to travel from Earth to Mars, depending on orbital positions. This means a simple conversation between mission control and Mars astronauts involves waiting periods of 6 to 44 minutes for each exchange. Emergency situations become impossible to manage from Earth because by the time mission control receives a distress signal and formulates a response, the emergency will have resolved itself one way or another. Recent psychological studies conducted throughout 2025 have examined how these communication delays affect human performance and mental health during long-duration missions. The research reveals that astronauts experience increasing levels of stress and isolation as communication delays exceed 10 minutes each direction. Mars crews will need to develop unprecedented levels of autonomous decision-making capability and psychological resilience. Mission planners must design every procedure and protocol around the assumption that Earth cannot provide real-time guidance or support. The distance to Mars makes our quarter-million-kilometer journey to the moon seem like a short drive to the local grocery store. If you could drive a car at highway speed to Mars, the journey would take approximately 2,500 years of continuous driving. A commercial airliner flying at cruising altitude would need 32 years to cover the distance to Mars during closest approach, and 115 years when the planets are at maximum separation. The Apollo spacecraft that carried astronauts to the moon in 3 days would require between 150 and 1,100 days to reach Mars, depending on orbital positions and flight trajectory. Current Mars missions already struggle with data transmission challenges created by these vast distances. The Mars Reconnaissance Orbiter serves as a crucial communications relay, collecting data from surface rovers and transmitting it back to Earth during specific time windows when orbital geometry allows for optimal signal strength. Each data transmission session must be carefully scheduled around planetary positions, solar interference, and limited power availability of spacecraft systems. The Perseverance rover can only communicate directly with Earth for a few hours each day. And even then, data transmission rates are thousands of times slower than your home internet connection. Emergency scenarios on Mars present challenges that no human mission has ever faced before. If a Mars astronaut suffers a medical emergency, mission control on Earth will not know about it for up to 22 minutes. After doctors and engineers spend time analyzing the situation and developing a response plan, their instructions will take another 22 minutes to reach Mars. In the best-case scenario with minimal communication delay, a Mars medical emergency will receive Earth-based guidance after a 6-minute delay. In worst-case scenarios, Mars astronauts must handle life-threatening situations completely independently for nearly an hour before any help from Earth can even begin to arrive. The psychological impact of this isolation extends beyond emergency situations into daily routine of Mars operations. Earth-based mission controllers cannot provide real-time guidance for complex tasks like equipment repairs, scientific experiments, or navigation decisions. Mars astronauts must possess the knowledge and skills to handle every possible situation that might arise during their 18-month stay on the planet's surface. They cannot rely on extensive ground support teams that have guided every previous human space mission since the beginning of the space program. Data collected by Mars rovers shows that dust storm seasons can block solar panels and disrupt radio communications for weeks at a time. During these blackout periods, Mars astronauts will lose all contact with Earth while dealing with reduced visibility, equipment malfunctions, and potentially life-threatening dust infiltration into their habitat systems. The combination of communication delay and periodic communication blackouts creates scenarios where Mars crews must be completely self-sufficient for extended periods. The energy requirements for communicating across Mars distances stress every component of communication systems. Mars rovers must use large high-gain antennas and powerful transmitters to send signals across the solar system. Even with these powerful systems, data transmission rates are measured in bits per second rather than the megabits per second that we take for granted in Earth-based communications. A single high-resolution photograph from Mars takes hours to transmit to Earth, and video transmissions are essentially impossible except in highly compressed formats. Mars represents humanity's next giant leap into cosmic isolation because it pushes us beyond the range of practical real-time support from Earth. Every previous human space mission, including the Apollo lunar landings, maintained the ability for mission control to provide immediate guidance and support. Mars breaks this connection and forces human space travelers to operate with true independence for the first time in the history of space exploration. The 2025 mission planning documents reveal that Mars astronauts will carry medical supplies and equipment capable of performing surgical procedures without guidance from Earth-based doctors. They will have manufacturing equipment to produce replacement parts for critical life support systems. They will carry enough food, water, and breathing supplies to survive for months longer than their planned mission duration. Mars missions require a level of self-sufficiency that makes the International Space Station look like a suburban house with city utilities. Yet even this incredible distance to Mars, spanning hundreds of millions of kilometers and requiring years of travel time, represents just our first real step beyond Earth's immediate neighborhood. The distances we have sent our most ambitious robotic explorers reveal scales that make even Mars seem close to home. Voyager's incredible journey continues. Voyager 1 sits 24.47 billion kilometers away from Earth right now, traveling through the space between stars at 61,198 kilometers per hour. This spacecraft launched in 1977 and has been flying away from Earth for 48 years without stopping once. Voyager 1 crossed into interstellar space in August 2012, becoming the first human-made object to leave the influence of our sun's solar wind and enter the realm between stars. Voyager 2 followed this achievement in November 2018, crossing the same boundary at a different location and confirming that the space between stars contains mysteries we never expected. The data streaming back from both spacecraft reveals that interstellar space is not empty, as scientists once believed. Instead, this region contains magnetic fields, cosmic rays, and charged particles that behave in ways that challenge our understanding of physics. Voyager 1 detected unexpected increases in cosmic ray intensity and strange magnetic field orientations that suggest the interstellar medium has structure and complexity that we are only beginning to understand. These discoveries came from a spacecraft that weighs just 773 kilograms and carries scientific instruments that weigh only 105 kilograms total. When Voyager 1 transmits data back to Earth, those radio signals travel at the speed of light for 23 hours and 14 minutes before reaching the massive antennas of NASA's Deep Space Network. Every command sent to Voyager 1 takes 23 hours and 14 minutes to arrive at the spacecraft, and confirmation that the spacecraft received and executed that command takes another 23 hours and 14 minutes to travel back to Earth. This means that controlling Voyager 1 requires nearly 2 full days for each interaction, and any problem that develops on the spacecraft happened almost a day before engineers on Earth learn about it. The spacecraft systems are failing in ways that create urgent time pressure for the mission teams. Voyager 1's primary roll thrusters stopped working in 2004 after losing power in 2 small internal heaters, and engineers determined the broken heaters were likely unfixable. They switched to backup roll thrusters to keep the spacecraft's antenna pointed toward Earth. But those backup thrusters started showing problems by 2020. The fuel tubes are experiencing a buildup of residue that could cause them to stop working completely, which would end the mission because the spacecraft would lose its ability to point its antenna toward Earth. Engineers faced a race against time to revive a set of thrusters that had been dormant since 2004. The solution required turning on the dormant roll thrusters and restarting the broken heaters, but this created a dangerous situation. If the spacecraft star tracker drifted too far from its guide star while the heaters were off, the dormant thrusters would automatically fire and could trigger a small explosion. The team had to get the star tracker pointed as precisely as possible before attempting the repair, and they faced additional time pressure because Deep Space Station 43 in Canberra, Australia, would be offline for upgrades from May 2025 through February 2026. On March 20th, 2025, engineers watched as Voyager 1 executed their repair commands. Because radio signals take over 23 hours to travel from the spacecraft to Earth, everything they observed had actually happened almost a day earlier. Within 20 minutes of receiving the spacecraft's response, the team saw the temperature of the thruster heaters rise dramatically and knew they had succeeded in reviving systems that had been dead for 21 years. Voyager 1 travels at what seems like incredible speed, covering 61,198 kilometers every hour. But this velocity is actually crawling when measured against cosmic distances. At its current speed, Voyager 1 would need 73,000 years to reach Proxima Centauri, the nearest star to our Sun. The spacecraft moves so slowly on galactic scales that the stars themselves will have moved to different positions in the sky by the time Voyager 1 travels significant distances toward them. The galaxy rotates around its center, carrying our entire solar system through space much faster than Voyager 1 can travel away from us. The famous pale blue dot photograph, taken by Voyager 1 in 1990 when it was 6 billion kilometers from Earth, shows our planet as a tiny speck suspended in a sunbeam. From today's perspective, with Voyager 1 now 4 times farther away, Earth would appear even smaller and dimmer in the cosmic darkness. This image captured the entire human experience as a single pixel of light, revealing how small our world appears even from within our own solar system. Voyager 2 continues its parallel journey through interstellar space, currently located 20.43 billion kilometers from Earth and traveling at 55,347 kilometers per hour. This spacecraft crossed the heliopause boundary in November 2018, entering interstellar space at a different location than Voyager 1 and providing scientists with comparative data about the boundary between our solar system and the space between. Stars. Voyager 2's measurements revealed that the heliopause has a different shape and magnetic field orientation than Voyager 1 encountered, suggesting that our solar system's boundary with interstellar space varies significantly in different directions. Both spacecraft will eventually lose contact with Earth as their power sources continue to weaken and their systems fail one by one. The radioisotope thermoelectric generators that power both Voyagers lose about 4 watts of power each year, and mission planners must regularly shut down non-essential systems to conserve power for the most important scientific instruments. Current projections suggest that Voyager 1 will lose the ability to transmit data back to Earth sometime between 2025 and 2030, depending on how quickly its remaining systems degrade. Despite traveling for 48 years and reaching distances that dwarf anything humans have ever achieved, both Voyager spacecraft remain well within the gravitational influence of our Sun. NASA calculations indicate that Voyager 1 will not truly exit the solar system until it emerges from the Oort cloud in another 14,000 to 28,000 years. The Oort cloud is a spherical shell of icy objects that surrounds our solar system at distances ranging from 2,000 to 100,000 astronomical units from the Sun. This means that Voyager 1, despite its incredible 48-year journey into interstellar space, has traveled less than 1% of the distance to the true edge of our solar system's gravitational influence. The Voyager spacecraft continue to rewrite our understanding of the space between stars, while simultaneously revealing how vast the distances are even within our own cosmic neighborhood. Yet these record-breaking distances pale in comparison to the gaps that separate us from the thousands of worlds that astronomers have discovered orbiting other stars. New worlds beyond our solar system. Since 2020, astronomers have discovered over 7,000 confirmed exoplanets orbiting stars beyond our solar system. And each new discovery reveals worlds separated from us by distances that make interplanetary travel look like a short walk around the block. These alien worlds orbit their stars in the same way that Earth orbits the Sun, but they exist in a realm so far away that the light we see from their parent stars left those systems years or decades ago. When you look up at the night sky and see a star that hosts an exoplanet, you are literally looking back in time at light that began its journey to Earth before you were born. The 2025 exoplanet surveys have identified potentially habitable worlds that could support liquid water on their surfaces. But these tantalizing targets sit at distances that challenge every assumption about space travel and human exploration. Gliese 12b, discovered in January 2025, sits 40 light-years away from Earth and represents the nearest transiting temperate Earth-sized world that astronomers have found. This planet receives similar amounts of energy from its star as Venus receives from our Sun, making it a prime candidate for detailed atmospheric studies using the James Webb Space Telescope. However, the 40 light-years distance means that light from this world takes 40 years to reach us, and any signals we might send toward Gliese 12b would take 40 years to arrive there. Speculos 3b presents an even more intriguing target for scientific study. Located 55 light-years from Earth, this planet is tidally locked to its parent star, meaning one side permanently faces the star while the other side remains in eternal darkness. The day side experiences scorching temperatures, while the night side freezes in perpetual cold. But the boundary zone between these extremes might harbor conditions suitable for liquid water and potentially life. The Speculos project continues to monitor this world using ground-based telescopes, but every observation shows us what happened 55 years ago due to the time it takes light to travel across these vast distances. Proxima Centauri b orbits the nearest star to our Sun at a distance of 4.24 light-years, making it our closest known exoplanetary neighbor. This world sits within the habitable zone of its red dwarf star, where temperatures might allow liquid water to exist on its surface. Recent studies suggest that Proxima Centauri b might have a substantial atmosphere and possibly even oceans. But confirming these characteristics requires observations that push our most advanced telescopes to their absolute limits. The 2025 data indicates that this planet experiences intense stellar flares from its parent star, which could strip away atmospheric gases and sterilize the surface. These flares occur unpredictably and with such violence that they might make the planet uninhabitable despite its location in the theoretically habitable zone. Current rocket technology would require over 73,000 years to reach Proxima Centauri b, assuming we could build a spacecraft that maintains the same velocity as Voyager 1 throughout the entire journey. The energy requirements for achieving higher speeds increase exponentially with velocity, creating engineering challenges that exceed the capabilities of entire civilizations. Accelerating a single kilogram of matter to just 10% of light speed would require energy equivalent to the entire annual power output of the United States. Accelerating a spacecraft large enough to carry human passengers to these speeds would require energy resources that exceed the total power generation capacity of our entire planet. The Breakthrough Starshot project proposes using powerful laser arrays to accelerate tiny lightweight probes to 20% of light speed, which would reduce the travel time to Proxima Centauri to approximately 20 years. These probes would weigh just a few grams and carry miniaturized cameras, sensors, and communication equipment. The laser system required for this mission would need to generate 100 gigawatts of power, equivalent to the output of about 100 nuclear power plants, focused into a beam precise enough to push these tiny spacecraft across interstellar distances. Even if this technology succeeds, the probes would pass by Proxima Centauri at such high speed that they would have only minutes to collect data and transmit it back to Earth before continuing into the void beyond. The James Webb Space Telescope has revolutionized our ability to study exoplanet atmospheres by detecting the chemical signatures of gases surrounding these distant worlds. In April 2025, JWST detected potential signs of dimethyl sulfide and dimethyl disulfide in the atmosphere of K2-18b, molecules that could indicate biological processes. However, subsequent analysis by 3 independent research teams revealed that these molecules can form through non-biological processes, highlighting the complexity of interpreting chemical signatures across interstellar distances. Dr. Luis Wellbanks from Arizona State University noted that while these detections represent significant technical achievements, they do not provide conclusive evidence for extraterrestrial life. Recent discoveries suggest that planet formation occurs around a wide variety of star types and in diverse configurations that challenge our understanding of planetary systems. In May 2025, astronomers using the European Southern Observatory's Very Large Telescope captured images of a planet forming around a young star, revealing a structured disk that extends 130 astronomical units from the parent star. This forming planet appears to be a gas giant several times more massive than Jupiter, and the team plans to use the James Webb Space Telescope to attempt direct imaging of this world as it accumulates material from the surrounding disk. NASA's spacex observatory, scheduled for launch in 2025, will survey over 450 million galaxies and 100 million stars in our own galaxy, creating the most comprehensive map of the universe ever attempted. This mission will search for water and organic molecules in stellar nurseries where new stars and planets form, helping astronomers understand how frequently Earth-like worlds develop around other stars. The data from spacex will reveal whether the conditions that led to life on Earth occur commonly throughout the galaxy or represent an extremely rare combination of circumstances. Even our nearest stellar neighbors, sitting just a few light years away, exist in a realm of distance and isolation that makes them effectively unreachable using any technology that humans can currently imagine. These stars represent the beginning of our galactic neighborhood, but they are separated from us by voids so vast that crossing them would require technological capabilities and energy resources that exceed anything our civilization has ever achieved. The exoplanets orbiting these nearby stars might harbor life, water, and conditions similar to Earth, but they remain as inaccessible to us as if they existed in a completely different universe. Yet all of these distant worlds, scattered across dozens of light years, exist within the same galaxy as Earth, and our attempts to reach them or communicate with them create signals that spread
our galaxy's
outward into the
Census.
cosmic darkness. The expanding sphere of human radio signals represents our entire presence in the galaxy. Yet it covers less than 0.0002% of the Milky Way's total volume. Right now, every radio and television broadcast that humanity has ever transmitted travels away from Earth at the speed of light, creating a bubble of our civilization's signals spreading through space. This radio bubble started in the 1930s when we first began broadcasting powerful radio transmissions, and by 2025 it has grown to encompass a sphere roughly 190 light years in diameter. Within this bubble, any alien civilization with sensitive enough equipment could detect our sitcoms, news broadcasts, and music from decades past. Lucy and Ricky Ricardo's voices from I Love Lucy are currently passing through star systems 70 light years away, while the Beatles' music from the 1960s reaches stars located about 60 light years from Earth. The most powerful radio transmissions we have ever sent, including the Arecibo message beamed toward the globular cluster M13 in 1974, have traveled just 51 light years from Earth. These deliberate attempts to communicate with extraterrestrial intelligence represent our strongest signals, but even they have reached only a microscopic fraction of our galaxy. The radio telescopes that could detect these signals from similar distances would need to be enormous and precisely aimed, making the chances of accidental detection extremely small. Most of our radio leakage, like television broadcasts and cell phone signals, becomes undetectable at distances of just a few light years due to the inverse square law that governs signal strength. Beyond this 190 light-year radio bubble lies absolute silence, as far as human civilization is concerned. The vast majority of our galaxy has no idea that Earth exists, that life evolved here, or that an intelligent species has developed technology and begun transmitting signals into space. The silence extends in all directions, encompassing billions of stars and trillions of planets that remain completely unaware of our presence. The 2025 galactic census reveals that our Milky Way contains approximately 400 billion stars, significantly more than earlier estimates of 100 to 200 billion. Advanced infrared surveys and gravitational microlensing studies have identified previously hidden populations of red dwarf stars and brown dwarf objects that were invisible to older detection methods. These updated counts suggest that our galaxy hosts between 800 billion and 3.2 trillion planets, with Earth-sized worlds numbering in the tens of billions. Statistical analysis indicates that roughly 300 million planets in our galaxy might have conditions suitable for liquid water and potentially life. Recent mapping projects have revolutionized our understanding of the Milky Way's structure and our location within it. The European Space Agency's Gaia mission has measured the precise positions and motions of over 1.8 billion stars, revealing that our galaxy has a complex four-armed spiral structure rather than the two-armed structure that astronomers believed for decades. Earth sits within the Orion Arm, also called the local arm, which extends about 10,000 light years in length and lies between the major Sagittarius and Perseus spiral arms. Our position, roughly 26,000 light years from the galactic center, places us in what astronomers call the galactic habitable zone, where conditions favor the formation of rocky planets and the development of complex chemistry. The scale of our galaxy dwarfs every distance we have discussed so far. The Milky Way measures approximately 100,000 light years in diameter, meaning that light from stars on the opposite side of the galaxy takes 100,000 years to reach us. When you look toward the constellation Sagittarius and see the bright band of the Milky Way, you are seeing light from stars that were shining when anatomically modern humans first appeared on Earth. The galaxy contains so much empty space that if you could shrink it down to the size of North America, our entire solar system would be smaller than a coin, and the nearest star would be another coin located several miles away. The supermassive black hole at our galaxy center, designated Sagittarius A*, has been the subject of intense study throughout 2025. This gravitational monster contains the mass of 4.15 million suns, compressed into a region smaller than Mercury's orbit around the Sun. The Event Horizon Telescope collaboration has continued to monitor this black hole, capturing images that show matter spiraling into the event horizon at speeds approaching the speed of light. The black hole's gravitational influence extends across thousands of light years, controlling the orbits of millions of stars near the galactic center and helping to maintain the galaxy's overall structure. Recent observations have detected massive stars orbiting Sagittarius A** in elliptical paths that bring them within 120 astronomical units of the black hole's event horizon. These stars experience gravitational forces so intense that time itself slows down measurably compared to the rate of time passage here on Earth. The star designated S62 completes one orbit around the black hole in just 9.9 years, reaching speeds of 7,650 kilometers per second at its closest approach. These orbital measurements allow astronomers to test Einstein's general relativity in the most extreme gravitational environment accessible to human observation. The Square Kilometer Array, with construction beginning in 2025, will be 50 times more sensitive than any existing radio telescope. This facility will be capable of detecting Earth-level radio emissions from distances of several hundred light years, potentially expanding our search for extraterrestrial intelligence across a volume of space containing millions of star systems. The array will also search for technosignatures, artificial signals that might indicate the presence of advanced civilizations, across frequency ranges that previous searches could not access. Our galaxy rotates like a massive pinwheel, with stars in different regions moving at different velocities around the galactic center. The Sun and our entire solar system orbit the galactic center at a speed of 828,000 kilometers per hour, completing one full orbit every 225 million years. This means that since Earth formed 4.5 billion years ago, our planet has completed approximately 20 trips around the galaxy. The last time we were in our current galactic position, dinosaurs ruled the Earth and flowering plants had not yet evolved. The Milky Way's rotation creates a cosmic perspective on time that makes human history appear instantaneous. Our entire recorded history, from the earliest written records to the present day, represents just 0.0000002% of one galactic year. All of human civilization, from the first cities to space exploration, has occurred while our solar system has moved less than 1/50,000th of the way around its galactic orbit. Yet this massive spiral galaxy, containing hundreds of billions of stars and trillions of planets, exists within a gravitational dance with neighboring galaxies that creates motion on scales that dwarf even galactic rotation. The local group's cosmic dance. The Andromeda Galaxy sits 2.537 million light-years away from us right now, moving directly toward the Milky Way at 250,000 miles per hour. This massive spiral galaxy contains over 1 trillion stars, making it roughly twice the size of our own galaxy, and every second that passes brings it 68 miles closer to us. The most recent calculations using data from the Hubble Space Telescope indicate that Andromeda and the Milky Way will begin their gravitational interaction in approximately 4.5 billion years from now. This collision timeline has been refined from earlier estimates that suggested the merger would occur in 4.8 billion years, meaning the event is approaching faster than astronomers previously thought. When you look up at the constellation Cassiopeia on a clear night away from city lights, the fuzzy patch of light you can see with your naked eyes is actually the Andromeda Galaxy. That light left Andromeda 2.537 million years ago, when early human ancestors were just beginning to use stone tools in Africa. The photons hitting your eyes tonight began their journey across space before Homo sapiens existed as a species. This galaxy appears as just a small smudge in our night sky, but it spans an area roughly 6 times wider than the full moon when viewed through powerful telescopes. Our local group contains 54 confirmed galaxies bound together by gravity within a region spanning roughly 10 million light-years in diameter. The Milky Way and Andromeda dominate this cosmic neighborhood as the 2 largest members. with Andromeda being the clear heavyweight in our galaxy ranking as the second most massive. The remaining 52 galaxies are mostly dwarf galaxies, including the large and small Magellanic Clouds that orbit our own galaxy like cosmic satellites. These smaller galaxies contain anywhere from a few million to several billion stars, making them significantly smaller than the major spiral galaxies, but still containing more stars than humans have ever counted. The gravitational dance between galaxies in the local group creates a complex web of interactions that astronomers are still working to understand. The Triangulum Galaxy, also known as M33, sits about 3 million light-years away and may eventually become part of the Andromeda Milky Way merger process. Computer simulations suggest that Triangulum could be captured by the gravitational interaction between the two larger galaxies, creating a three-way cosmic collision that would reshape the entire local group. The Andromeda Milky Way collision will unfold over approximately 2 billion years once the galaxies begin their gravitational interaction. The process will not resemble a violent crash, but rather a slow-motion cosmic ballet where the two galaxies pass through each other multiple times before finally settling into a single merged system. During the initial encounter, the galaxies will distort each other's spiral arms through tidal forces, flinging streams of stars across millions of light-years of space. Some stars will be ejected completely from the gravitational system and sent wandering through intergalactic space as cosmic refugees. Current simulations indicate that our solar system will likely survive the galactic merger intact, but it will be relocated to a completely different part of the merged galaxy. The Sun and Earth have a 50% chance of being moved to a region twice as far from the galactic center as we currently sit. This relocation would place us in a much quieter neighborhood with fewer nearby stars and a darker night sky. The other 50% chance involves our solar system being moved closer to the galactic center, where the night sky would be significantly brighter due to the higher density of stars in that region. Dark matter provides the invisible scaffolding that holds the local group together and determines how the galactic merger will proceed. Recent 2025 studies indicate that dark matter halos surrounding each galaxy extend far beyond the visible stars and contain roughly 5 times more mass than all the ordinary matter in the galaxies combined. These dark matter halos will merge first, creating a gravitational framework that guides the subsequent interaction between the visible galaxies. The night sky during the galactic merger will transform dramatically over the course of millions of human generations. Initially, Andromeda will appear as a bright, elongated cloud stretching across a significant portion of the sky, easily visible during daytime hours. As the galaxies interpenetrate each other, the night sky will be filled with spectacular stellar streams, glowing gas clouds, and regions of intense star formation triggered by the gravitational disruption. The merger will create one of the most active periods of star formation in either galaxy's history, illuminating vast regions of space with the light from newborn stars. During the peak of the merger process, the night sky could be bright enough to read by, with countless new stars forming in compressed gas clouds created by the galactic collision. These stellar nurseries will be visible as glowing nebulae scattered across the sky, creating a constantly changing tapestry of light and color. The increased stellar density during certain phases of the merger could result in close encounters between stars, potentially disrupting planetary systems and sending comets and asteroids on chaotic trajectories throughout the merged galaxy. The merged galaxy that will result from the Andromeda Milky Way collision has already been given a name by astronomers, Milky. This new galaxy will be an elliptical system containing roughly 1.4 trillion stars and spanning approximately 200,000 light-years in diameter. Milky will rank among the largest galaxies in our local region of the universe, but it will still be just one galaxy among the estimated 54 members of our local group's final configuration. The local group spans 10 million light-years in diameter, making it roughly 100 times larger than the individual galaxies it contains. This scale jump represents the same proportional increase that we see when comparing individual stars to planetary systems or planetary systems to entire galaxies. The gravitational binding energy that holds the local group together is enormous, requiring velocities of several hundred kilometers per second for any galaxy to escape the group's gravitational influence. Yet even this vast collection of 54 galaxies, spanning 10 million light years and containing trillions of stars, represents just a small component within much larger organizational structures that shape the architecture of the entire universe. Superclusters and cosmic architecture. The cosmic web represents the largest organizational structure in the universe, and since 2020, astronomers have created the most detailed maps of this vast network using data from millions of galaxies and sophisticated computer simulations. This web consists of massive filaments of dark matter and gas that stretch across hundreds of millions of light years, connecting galaxy clusters like threads in an enormous three-dimensional spider web. The filaments contain most of the universe's ordinary matter, while the spaces between them are vast cosmic voids that contain almost nothing at all. These mapping projects have revealed that the cosmic web follows predictable patterns, with galaxies forming where filaments intersect and absolutely nothing existing in the spaces between. The Laniakea supercluster contains our Milky Way Galaxy along with roughly 100,000 other galaxies spread across a region measuring 520 million light-years in diameter. This supercluster received its name in 2014, but the 2025 measurements have refined our understanding of its true boundaries and gravitational influence. Laniakea contains approximately 100 million billion stars, making it one of the most massive structures in our local region of the universe. Our local group of galaxies sits near the edge of Laniakea, in a relatively sparse region where the density of galaxies is much lower than in the supercluster's central regions. The entire structure has a mass equivalent to 100 million billion suns, and this enormous gravitational system influences the motion of every galaxy within its boundaries. The gravitational forces within Laniakea create a complex flow of galaxies moving toward regions of higher density. These galaxy flows follow predictable patterns, with galaxies streaming along the filaments of the cosmic web like water flowing downhill. The Milky Way participates in this cosmic flow, moving at a velocity of 2.3 million kilometers per hour toward the supercluster's center of mass. This motion occurs in addition to our galaxy's individual motion through space, creating a complex trajectory that carries us through the cosmic web along with tens of thousands of neighboring galaxies. The gravitational influence of Laniakea extends far beyond its visible boundaries, affecting galaxy motions across distances of nearly 1 billion light years. The Great Attractor represents one of the most mysterious gravitational anomalies in our cosmic neighborhood, exerting a pull on galaxies across hundreds of millions of light years. This region contains a concentration of mass equivalent to tens of thousands of galaxy clusters, but much of it remains hidden behind the plane of our own galaxy, making direct observation extremely difficult. The Great Attractor sits roughly 250 million light years away from us, and its gravitational influence affects the motion of our entire local group of galaxies. Recent studies suggest that the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster, revealing layers of gravitational influence that extend across increasingly vast scales. The distribution of matter throughout the universe follows a pattern that resembles a three-dimensional web, with roughly 80% of the universe's volume consisting of cosmic voids that contain almost no galaxies at all. These voids are not completely empty, but they contain less than 10% of the average density of matter in the universe. The largest known void, called the Boötes void, spans 330 million light-years in diameter and contains almost no galaxies in a region that should contain approximately 2,000 galaxies based on average cosmic density. The filaments between voids contain most of the universe's galaxies, compressed into structures that are extremely long and thin compared to their width. Recent discoveries about cosmic voids have revealed that they play a crucial role in the evolution of the universe's structure. These voids are not static, empty regions, but rather dynamic systems that continue to expand and evolve over cosmic time. The expansion of voids pushes matter toward the surrounding filaments, creating higher density regions where galaxies cluster together. This process has been ongoing for over 13 billion years, gradually creating the cosmic web structure that we observe today. The largest voids continue to grow, pushing galaxies away from their centers and creating increasingly complex patterns of matter distribution across the universe. Computer simulations of cosmic evolution now incorporate billions of particles to model how the cosmic web formed and continues to evolve. These simulations begin with a nearly uniform distribution of matter shortly after the Big Bang and model how tiny density fluctuations grew over billions of years to create the large-scale structure we observe today. The simulations reveal that the cosmic web's basic structure was established within the first few billion years after the Big Bang, but the detailed patterns of galaxy distribution continue to evolve as matter flows along the filaments. Modern simulations can accurately predict the locations of galaxy clusters and voids across vast regions of space, confirming our understanding of the gravitational processes that shape cosmic structure. Supercluster movements are governed by the complex interplay between gravitational attraction and the expansion of space itself. While gravity pulls matter together along the filaments of the cosmic web, the expansion of space works to separate structures that are not gravitationally bound. Superclusters like Laniakea can maintain their coherence because their internal gravitational forces are strong enough to overcome the expansion of space within their boundaries. However, the distances between different superclusters continue to increase as the universe expands, creating an ever-growing separation between these massive structures. Even these massive superclusters, containing millions of billions of stars and spanning hundreds of millions of light years, represent merely small components of the observable universe's total structure. The observable universe contains an estimated 10 million superclusters, each comparable in size to Laniakea, distributed across a volume that spans 93 billion light-years in diameter. This means that our local supercluster, despite its incredible size and mass, occupies approximately 1/10,000,000th of the observable universe's total volume. The cosmic web extends to the very edges of what we can observe, but the most powerful telescopes ever built are now revealing what lies at those distant boundaries. The Observable Universe's 2025 Census. The James Webb Space Telescope captured this image in 2024, and what you're looking at represents the deepest view into space that human technology has ever achieved. This single photograph shows galaxies that existed when the universe was only 400 million years old, which means the light from these distant objects has been traveling toward us for over 13.4 billion years. When you examine this image closely, every single point of light represents an entire galaxy containing hundreds of billions of stars. The galaxies appear as they existed billions of years before Earth even formed, giving us a direct view into the cosmic past that reveals how the universe looked when it was still in its infancy. Recent surveys using data from both the James Webb Space Telescope and the Hubble Space Telescope have updated our count of galaxies in the observable universe to at least 2 trillion separate galaxy systems. This number represents a significant increase from earlier estimates that suggested the universe contained only a few 100 billion galaxies. Each of these 2 trillion galaxies contains an average of 100 billion stars, though the largest galaxies can contain over 1 trillion stars, while the smallest dwarf galaxies might have only a few million. The mathematical calculation becomes almost incomprehensible when you multiply 2 trillion galaxies by 100 billion average stars per galaxy, yielding a total of approximately 200 billion trillion stars in the observable universe. The observable universe measures approximately 93.5 billion light-years in diameter, but this measurement creates confusion because the universe is only 13.8 billion years old. The expansion of space itself explains this apparent contradiction. When light left the most distant galaxies we can observe, those galaxies were much closer to us than they are today. Space has been expanding continuously since the Big Bang, carrying those distant galaxies away from us while their light traveled through the expanding universe to reach our telescopes. The galaxies that emitted the light we see today have moved much farther away during the billions of years their light took to reach us. This cosmic horizon represents the fundamental limit of what we can observe, creating a boundary beyond which we cannot see regardless of how powerful our telescopes become. The cosmic microwave background radiation marks this boundary, representing the moment when the universe became transparent to light approximately 380,000 years after the Big Bang. Before this moment, the universe was filled with a hot, dense plasma that absorbed and scattered light, making it impossible for us to observe directly. The cosmic microwave background provides our earliest possible view of the universe, appearing as a nearly uniform glow of radiation that fills the entire sky when observed at microwave frequencies. Galaxy formation in the early universe occurred much more rapidly than astronomers expected before the James Webb Space Telescope began operating. Observations from 2024 and 2025 have revealed fully formed galaxies existing just 500 million years after the Big Bang, suggesting that the first stars and galaxies assembled much faster than previous models predicted. These early galaxies appear surprisingly massive and well-organized, containing supermassive black holes and complex stellar populations that should have required billions of years to develop according to earlier theories. The discovery of these mature early galaxies has forced astronomers to revise their understanding of how quickly cosmic structures can form. Gravitational wave detections provide an entirely independent method for measuring cosmic distances and studying the universe's expansion. The LIGO and Virgo collaborations have detected over 90 gravitational wave events since 2015, mostly from black hole mergers and neutron star collisions. These events allow astronomers to measure distances to their sources without relying on traditional astronomical techniques like observing starlight. When gravitational wave events occur simultaneously with observable light emissions, they create standard sirens that provide precise measurements of cosmic expansion rates. The cosmic microwave background radiation analysis has reached unprecedented precision through missions like the Planck satellite and ground-based observatories. The 2025 analysis of cosmic microwave background data reveals temperature fluctuations that are accurate to within a few millionths of a degree. These tiny temperature variations represent the seeds that grew into the large-scale structure we observe today, including galaxy clusters, superclusters, and cosmic voids. The statistical properties of these fluctuations confirm that the universe is geometrically flat, meaning that parallel lines remain parallel across cosmic distances. When astronomers calculate the total number of stars in the observable universe, they arrive at a figure that exceeds the number of grains of sand on all beaches across the entire Earth. The current estimate suggests approximately one followed by 24 zeros individual stars exist within the volume of space that we can observe. This calculation multiplies the estimated 2 trillion galaxies by an average of 100 billion stars per galaxy. Though the uncertainty in both numbers means the actual count could be several times higher or lower. Each of these stars represents a potential solar system, with current estimates suggesting that most stars host at least one planet. Recent observations suggest that the observable universe represents only a tiny fraction of the total universe that exists beyond our cosmic horizon. Theoretical models based on cosmic inflation theory predict that the actual universe extends far beyond what we can observe, potentially by factors of millions or billions. The regions beyond our observable universe are forever hidden from us because light from those regions has not had enough time to reach Earth since the Big Bang occurred. The rate of cosmic expansion continues to accelerate due to dark energy, which means that galaxies currently visible at the edge of our observable universe will eventually disappear from view as they are carried away by expanding space faster than light can travel. This cosmic isolation represents the ultimate fate of any civilization that survives long enough to witness the universe's continued expansion. Yet this 93.5 billion light-year sphere that contains everything we have ever detected may itself be just a microscopic portion beyond of something far more vast. The accelerating expansion of space creates permanent barriers between distant regions that can never be crossed regardless of technological advancement. Space continues to expand at accelerating rates due to dark energy, carrying distant regions away from us faster than light can travel between them. This means that light from some regions of the universe will never reach Earth, even if we wait for infinite amounts of time. The cosmic horizon represents an absolute boundary beyond which we can never observe, visit, or communicate, creating permanent isolation between different regions of reality. Cosmic inflation theory explains why the universe beyond our observation extends to such incomprehensible scales. Dr. Alan Goose's refinements to inflation theory throughout 2025 have confirmed that the universe underwent a period of exponential expansion that began approximately 10 to the 37th of a second after the Big Bang. During this incredibly brief moment, the universe expanded faster than the speed of light, not because matter was moving through space at impossible velocities, but because space itself was expanding at exponential rates. This expansion phase lasted for an almost immeasurably short period, but it had consequences that affect the structure of reality on the largest possible scales. The calculations based on updated inflation models reveal numbers that strain human comprehension. If cosmic inflation began at 10 to the 37th of a second after the Big Bang, and the size of the universe before inflation equaled its age multiplied by the speed of light, then the entire universe could be approximately 150 sextillion times larger than our observable universe. This means that for every cubic meter of space that we can observe through our most powerful telescopes, there are 150 sextillion cubic meters of space that remain forever hidden from us. The mathematics of this scale become so extreme that they lose all practical meaning for human understanding. These vast scales create the theoretical possibility that infinite space contains infinite versions of everything we know. If the universe extends infinitely beyond our cosmic horizon, and if matter is distributed randomly throughout that infinite space, then statistical mechanics suggests that every possible arrangement of matter must occur somewhere. This means there could be infinite copies of Earth, infinite versions of every human being who has ever lived, and infinite variations of every event that has ever occurred. The concept challenges our understanding of uniqueness and individuality by suggesting that everything we consider special about our existence might be repeated countless times across infinite space. Recent theoretical work on multiverse concepts has expanded beyond the simple idea of multiple universes to explore the mathematical structures that might govern reality at the largest scales. These theories suggest that our universe might be embedded within higher dimensional spaces that contain other universes with completely different physical laws and constants. Some models propose that universes branch off from each other continuously, creating an infinite tree of realities where every possible quantum event spawns new universes. Other theories suggest that universes exist as bubbles within an infinite foam of space-time, each bubble containing its own version of physics and chemistry. The implications of multiverse theories extend far beyond academic mathematics into fundamental questions about the nature of existence itself. If infinite universes exist with every possible combination of physical laws, then our universe's apparent fine-tuning for life becomes statistically inevitable rather than requiring special explanation. The precise values of fundamental constants that allow stars, planets, and life to exist would occur naturally in some universes while being impossible in others. We find ourselves in a universe capable of supporting life because universes incapable of supporting life contain no observers to notice their existence. Studies of the ultimate fate of our universe reveal that cosmic expansion will continue accelerating indefinitely, driven by dark energy that comprises roughly 70% of all energy in the universe. This acceleration means that galaxies currently visible at the edge of our observable universe will eventually disappear from view as they are carried away by expanding space faster than their light can reach us. In approximately 150 billion years, only gravitationally bound local structures will remain visible, while the rest of the universe fades into unobservable darkness. The cosmic microwave background radiation will be stretched to wavelengths so long that it becomes undetectable, erasing the last traces of the Big Bang from our observational capabilities. Future telescope projects promise to push our observational boundaries closer to the absolute limits imposed by the cosmic horizon. The James Webb Space Telescope's successor missions planned for the 2030s will observe galaxies that existed just 200 million years after the Big Bang, approaching the moment when the first stars began shining. Ground-based telescopes, with mirrors exceeding 100 meters in diameter, will resolve individual stars in galaxies billions of light years away. Radio telescope arrays spanning entire continents will detect gravitational waves from the earliest moments of cosmic inflation. Yet even these technological marvels will only marginally expand the observable universe, while the vast majority of reality remains forever beyond our reach. The scale comparison between our observable universe and the true extent of reality resembles a light bulb sitting inside a volume larger than the former planet Pluto. If you placed a standard light bulb at the center of Pluto and let it represent our entire observable universe, the actual universe would extend far beyond Pluto's surface in all directions. This comparison actually understates the true scale because Pluto measures only about 2,400 kilometers in diameter, while the calculations suggest the actual universe could be trillions upon trillions of times larger than even this comparison suggests. The universe beyond our cosmic horizon contains wonders, civilizations, and phenomena that we will never discover or understand. Entire clusters of galaxies, each containing trillions of stars and countless planets, exist in regions of space so distant that their light will never reach Earth. Advanced civilizations might have developed technologies that surpass our wildest imagination, but they remain forever isolated from us by the fundamental structure of space-time itself. The greatest discoveries and most profound mysteries of existence might lie just beyond our cosmic horizon, tantalizingly close yet absolutely unreachable for all eternity. Every discovery that reveals the universe's true scale simultaneously demonstrates both our cosmic insignificance and the magnificence of human scientific achievement. These measurements place us as temporary arrangements of atoms on a small world orbiting an ordinary star in an unremarkable galaxy within an observable universe that represents essentially nothing compared to what actually exists. Yet this cosmic insignificance makes every human relationship, every moment of connection, and every act of kindness infinitely more precious. We are the universe becoming aware of itself, capable of measuring cosmic scales and understanding our place within them. The James Webb Space Telescope continues operating. The Artemis program targets lunar return by 2027, and infinite mysteries await our exploration together across the vast cosmos.